Okay, so I'm going to give a bit of context about what I'm about to show you. So initially what I wanted to do for Christmas was to film 12 videos again, similar to what I did last year for 12 Days of Christmas. But this year was going to make it more science themed. And I was filming the 7th video, which was going to be about 7 SI base units. And halfway through filming, I think I was explaining what how the second was defined. And I just thought, you know, I didn't really want to do this anymore. And so I wasn't really enjoying making like these 12 videos as much as I initially thought I would have. It was becoming more like a piece of work than just something I was going to do for fun. And so I decided to halt the whole 12-day video idea. And I haven't thought of a new Christmas video idea yet, but hopefully I will. I have about 6 days left. Today's the 19th, the day I'm filming. I just really needed to like just talk about it now rather than talk about it later. And so what I'm going to show you are 4 of the 12 videos, which I've actually finished editing. And yeah, so even though it doesn't make it to the main 12 days video, and which will probably never get made, here they are, and enjoy. Now at Random Maths Inc, this time last year, we did a series called 12 Days of Mathematical Christmas. And because I sort of ran out of Christmas video ideas again, I'm going to pretty much do the whole 12 days thing again. But with 2 changes. One, because I sort of did all the math topics that there was to do. Instead, I'm going to be doing it slightly differently this year. Rather than doing mathematical topics, we're going to be doing topics from various branches of science. I know this channel is called Random Maths Inc, right? And you just got to deal with it. And secondly, rather than doing a descending order like last year, we're going to be doing the countdown in ascending order. So I'm going to start with 1 today, and then we're going to go all the way until day 12, where I do the number 12. And so without any further ado, let's start the 12 days of scientific Christmas. And on day 1, we have one Carl Friedrich Gauss. Now, Gauss is probably one of the greatest mathematicians to ever live. He made so much contributions to various fields in both mathematics and of science. Now, Gauss was born in 1777 in a German city called Brunswick, although he initially did not know his exact birth date. All he did know, though, was that he was born 39 days after Easter. And so, because he didn't know his birth date, and he was probably quite curious to find out his birth date, he ended up making an entire algorithm to work out when Easter falls in each of the calendar years. And from that, he was able to find out when he was born. Now, as a kid, Gauss was a child prodigy. According to the tales from the past, once Gauss was asked by his maths teacher in a maths class to add up all the numbers from 1 to 100, and Gauss did it almost instantly and a lot quicker than all of his other classmates, and also getting the right answer. Well, how did he do this? Well, he realized that the numbers 1 to 100 can form 50 different pairs, which each of the pairs add up to 101. And so 50 pairs of 101, that gives you the answer of 5050, which Gauss is able to figure out when he was really young, which is absolutely amazing. Now, as I mentioned earlier, Gauss eventually grew up to become a mathematician who made loads and loads of contributions to different fields of both mathematics and to physics. And the more you study physics or mathematics, the more you start to see Gauss's name popping up in random places, which just shows you how much work he's done towards all the different fields. For example, if you've ever done statistics, you'll have probably came across the normal distribution, whose other name is the Gaussian distribution. And if somehow you want to integrate the area under the normal distribution curve or the Gaussian distribution curve, then you can perform something called the Gaussian integral, which I have actually dedicated an entire video to. You could check it out, probably leave the link somewhere on the screen. Now, if you've done linear algebra before, you'll know that when you solve a system of equations, what you can initially do is try to turn this matrix into a triangular matrix using a method called Gaussian elimination. And if you then want to go on and solve this system of equations, you can continue by making this triangular matrix a diagonal matrix. This whole process is called the Gauss-Jordan method. Now, if you hate this method of solving linear equations, you can use a different approach where you can try to solve the equations numerically. And this method is called the Gauss-Seidel method. Now, if you've done electricity and you've studied about electric flux and electric fields, you would have learned that the amount of electric flux through a closed surface will be proportional to the amount of charge surrounded by that closed surface. And guess what that law is called? Yep, it's called Gauss's law. And interestingly, Gauss's law even have different forms for gravitational fields and flux, and also for magnetic field and magnetic flux. Magnetic flux, interestingly enough, also has a very interesting unit called the Gauss. And there are so many other things which are named after Carl Friedrich Gauss. In fact, there is an entire Wikipedia article which lists out all of these different things which was named after Gauss. You could go check it out. I'll leave a link somewhere on the screen again. But anyways, that is it for the first day of Christmas. There is one Carl Friedrich Gauss. Welcome to the second day of Scientific Christmas, and today we have two postulates of special relativity. We all know special relativity, right? That thing with time dilations and length contractions and E equals mc squared. Special relativity deals with the relationship between space and time, and it's an improvement from classical physics in the sense that it actually considers what happens to objects which are moving close to the speed of light. Now, the whole theory of special relativity is based upon two rules, or we call two postulates, which is drawn up by this obscure German scientist called Albert Einstein in 1905. Now, the first postulate of special relativity basically just says that the laws of physics is the same in all inertial frames of references. But what do you even mean by that? Well, let's give an example. Let's consider something like the laws of conservation of momentum. You know it, right? That the momentum before a particular collision must be the same as the momentum after the collision. So let's say you are on Earth and you have two balls and you decide to collide them against each other. Now, you can measure the velocities of the two balls before it collides with each other, and you can measure the velocities of the ball after it collides with each other. And then you can try to use conservation of momentum to test the situation out, and you'll find that the momentum will be conserved within the system and the physics works. But then let's say your friend is in a car driving past you while you are doing the experiment. Now, what he could do is he could also try to measure the velocities of the ball before and after the collision. But now, he won't be able to record the same velocities of the ball as you did. However, if he then uses the conservation of momentum equation and try to apply that on the system that he observes, he will still get the right answers. He will still conclude that conservation of momentum still makes sense to him, even though you two did not measure the same velocities of the ball with each other. Or basically, it doesn't actually matter how you measure a physical system, because the laws of physics should still be true regardless of the frame of reference which you are observing a particular situation from. Here's another way you can think of the first postulate of special relativity. Imagine I'm locked in a car and I can't see what's actually happening outside. There is no physics experiment that I can perform that will help me determine whether that car is stationary or is moving at some velocity with respect to the ground outside. In other words, if I was in the car and I was trying to bounce a table tennis ball, it will look exactly the same to me whether the car is stationary or whether the car is moving at a constant velocity. Now, this postulate isn't particularly new to special relativity or anything. It's already quite established since Galilean relativity. The key difference between classical relativity and special relativity is the second postulate. Now, the second postulate of special relativity says that the speed of light is constant regardless of the speed of the observer relative to the source of the light. What this means is that, say, if you shine a flashlight on the ground, you can try to measure the speed of the light that comes out of the flashlight and you'll get some certain value. But then if your friend is in that same car again, driving past you, turning that flashlight on, and he tries to measure the speed of light that comes out of that flashlight, he will get the same speed as you. And just using classical physics, this doesn't seem to be true at all. And that's where Galilean relativity breaks down, and we need to use special relativity. And the speed of light being a constant is something that we can actually verify. There is an experiment called the Michelson-Morley experiment, which verifies that the speed of light is actually constant regardless of the speed of the observer. However, I don't have time to explain it now, and we have to end the video somewhere, so it might as well be here. Thank you very much for watching this video, and there are two postulates of special relativity. Now, I could have done a video on Newton's 3 laws of motion, but I think I've done that enough times already. So instead, I'm going to do something different. Instead, there are 3 domains of life. Taxonomy is a system of classification of living organisms into different groups, so that each group has got organisms which have similar features to each other. Now, there are many levels to this classification, but at the very top of the taxonomic rank is something called the domain. And all living organisms fit into one of 3 domains. They all fall under either domain Eukarya, domain Bacteria, or domain Archaea. Now, initially there were only 2 domains. All organisms are either a prokaryote or a eukaryote. Now, the key difference between eukaryotes and prokaryotes is that eukaryotes have got membrane-bound organelles. Things like the nucleus, or the Golgi body, or the chloroplast if you're a plant, or the powerhouse of a cell, all these things which prokaryotes did not have. And there are also other key differences between the cells of eukaryotes and prokaryotes. Like, eukaryotes have got linear chromosomes and they have ATS ribosomes, and their cells reproduce through means of mitosis or meiosis. Whereas cells of prokaryotes mostly have circular chromosomes and 70S ribosomes, and they also mostly reproduce through means of binary fission. Eukaryotes consist of most of the organisms that you associate with being organisms. Things like palm trees, or lions, or humans, or elephants, penguins, and platypuses, or platypi, I'm not really sure what their plural is. And prokaryotes consist of organisms like E. coli, which is a bacteria, or even that creature called Sulfobus, which lives in extremely hot and extremely acidic conditions. But then biologists weren't really happy with the classifications that they came up with and decided that they could do better. And so biologists looked at the prokaryotes that they've classified, and they realized that some of the prokaryotes that they grouped together were in fact too different, and so decided that they were better off in 2 different domains. And that's how domain Bacteria and domain Archaea was born. Now, the key difference between the cells of Archaea and bacteria is the structures of a molecule inside the cell called ribosomal RNA, which is a molecule which makes up an organelle called the ribosome, which is used to make proteins within the cell. And there are also other structural differences between bacteria and Archaea. For example, the cell walls of bacteria mostly are made of molecules called peptidoglycan, which consists of sugar and amino acids, whereas the cell wall of Archaea are mostly made of molecules called pseudopeptidoglycan. And Archaea most of the times are also found in much harsher conditions, such as in conditions of extreme temperature or extreme saline conditions. In fact, the first Archaea that was discovered by scientists were discovered near volcanoes, which are areas of extremely high temperature. And so then biologists end up with 3 different domains to put each of the organisms into. And that is just the beginning of the whole taxonomic system, but again, we don't have time to go into the rest of it. And so there we go. There are 3 domains of life. Now, as you can see, we're on the 4th day already, but I've been wearing the same shirt as the past 3 days. That's because I've done all the video filming all on the same day. But anyways, there are 4 laws of thermodynamics. Now, thermodynamics is the study of heat and energy of different physical systems, and there are 4 laws which governs the theory of thermodynamics. And like any good programming languages, the law starts at number 0. Now, the 0th law of thermodynamics states that if 2 systems are in thermal equilibrium with another system, in other words, there are no energy transfer between these systems whatsoever, then that means these 2 systems must be in thermal equilibrium with each other. Now, this law is able to help us define a rather important concept in physics, because if 2 systems are in thermal equilibrium with each other, then that means there must be some property of these systems which are the same between the 2 objects. And it's probably something to do with the sort of energy density or energy per particle within the system, which might be the same between these 2 systems, hence there are no energy exchanges. And this energy per particle is a very, very loose definition of what temperature is. Temperature is the measure of how hot and how cold a system is, but it more scientifically is the measure of how much kinetic energy is in the particles of a particular system. Now, the first law of thermodynamics is just basically a statement for conservation of energy in a system. And the first law, as Morty will put it, says that
the increment in the internal energy of a system is equal to the increment of heat supplied to the system. Wow!
In other words, it says that if you have a system, like for example, a gas in a piston, and you either do work to it or you heat up the system, then the internal energy of the system will change. And it will change equal amounts to how much work has been done to the system and how much heat is being applied onto the system. And so what this ultimately means is that you can't have a system which just keeps giving out energy without itself running out of energy. Otherwise, that would break the first law of thermodynamics. But now imagine this. Let's say you have a room and you take an ice cube and you put it in the room. What happens? Well, obviously, the ice cube will eventually melt, right? It would absorb the energy from the room, and the ice cube itself will start to heat up and have a higher temperature until it eventually becomes water when it becomes at a high enough temperature. And that's still okay because the energy within the room is still going to be the same because the ice cube just gains energy from absorbing it in the room, so the energy within the room itself will still be the same. However, what you will never see is the water somehow just losing all its energy, giving it back to the surroundings, and then becoming a block of ice again. And so for some reason, when ice is left in the room, it could turn into water, that's okay, but water can't go back turning into ice. And even though the first law of thermodynamics isn't broken in this case, we know that this physical phenomena still can't happen. And this is due to the second law of thermodynamics. Now, there's many ways that you can state the second law of thermodynamics, but one way that you can say it is that heat will never transfer from a colder place or a place of lower temperature to a hotter place or a place of higher temperature. But not all systems can be easily defined in terms of heat transfers. So we can define another property of physical systems called entropy, which sort of measures how disordered the system actually is. And so things like solids, where the particles are arranged in a much orderly manner, will have less entropy than something, for example, like a gas, where the particles just pretty much random. And the second law of thermodynamics can be stated using entropy. As Muse puts it, the second law of thermodynamics says that
in an isolated system, entropy can only increase.
Or in other words, physical systems will tend to a state of higher entropy and higher disorderedness, but never the other way around. And the third law of thermodynamics talks about something called absolute zero, which is when the temperature of a system is really, really, really low. The third law says that when a system is at absolute zero, the crystals within the system there will have zero entropy. Absolute zero can be thought of as the lowest temperature possible, and temperature is a sort of energy of the particles in a particular system. And so at absolute zero, the lowest temperature possible, the particles in that system pretty much basically has no energy and has no room to move around, and so it's basically as ordered as it would possibly be. It would be stationary, not even moving a single bit. And because it's not moving at all, it means there must be no degrees of disorder in the system at all. Hence, zero entropy. Now, if you want to know more about the 4 laws of thermodynamics, I recommend this playlist, which I'll link on the screen somewhere, by the Royal Institute. It's quite good. I sort of watched it as well to try to make this video. But anyways, this is all we have time for. There are 4 laws of thermodynamics.